try to be short. Okay, yeah, thank you for the introduction. My name is Christoph Stasch, and I will present our work on the development of an interoperable infrastructure for marine real-time observation data. We are from 52 Degrees North, which is a research organization from Germany. And we are doing applied research in the field of geoinformatics. And we did that work jointly in projects funded by the European Commission with Dick Sharp from Maris and also with Alexandra Kokinaki from the British Oceanographic Data Center, BODC. If you take a look on marine applications, we could see that there are a lot of different sensors that are involved in marine monitoring applications. So you could see that there are, for example, underwater gliders, there are buoys, there are sensors that are attached to boats or to ferries, for example. And these sensors are all, to make it a bit more complicated, operated by different organizations. And that means that we have a very heterogeneous landscape of data formats and access tools. And of course, the final goal of our aims is to provide an interoperable infrastructure that allows to easily integrate the data from different sensor sources, from different organizations, in order to facilitate an easy exchange of marine observation data between different organizations. Luckily, there is already a standard defined by the Open Geospatial Consortium for the exchange of observation data and also for the integration of observation data in spatial data infrastructures. And that is the Sensor Observation Service, which is a web service specification similar or comparable to the web coverage service, for example, or to the web feature service for feature data. And it's specifically designed for observation data. That means that it is relying on models and encodings for sensor metadata, that is SensorML, the sensor model language, and for observation data, that is the observation and measurement standard. And as you could see in the slide, the SOS is kind of a mediator between different observation networks and different applications. And people dealing with sensor data and environmental observations know that quite often you need to do data transformation first, so you need to see how the data is encoded, then transform it into another format. And the aim is to ease that burden, or to reduce that burden. INSPIRE already supports the sensor observation service and sensor observation data. So there are guidelines for the use of observation and measurements and sensor web enablement related standards in INSPIRE. And there's also a technical guidance document for implementing download services using the sensor observation service and filter encoding, which allows to define, for example, temporal filters on the sensor data. Well, with the marine application that we are currently working on, we think that this is a nice illustration how INSPIRE helps to deal with a broad range of different observation types, because as you could see in the introductory slides, there are very heterogeneous sensors resulting also in very heterogeneous observation data types. So there may be time series observations for fixed locations. For example, in case of buoys, we don't have any moving objects. We just have a fixed location in the time series. Then we may have research vessels and gliders. And these are classical trajectory observations. And then we may have more specific observations as well, like conductivity and temperature that are measured at different depths. And in this case, we get profile observations. So as you can see, there are lots of different ways how observations are gathered and are stored also and are published then to other data consumers. And the ongoing project demonstrates the applicability of this approach. We identified two challenges actually beyond the technical guidance document, and one is on the provision of sensor metadata. And we are therefore exploring ways how to use sensor model language to describe the different sensors that are applied in marine applications. And one obstacle that we identified is to provide kind of best practices how to publish existing observation data sets in such infrastructures, for example, in the sensor observation service. So, I mean, you still have to connect the sensors to a database or to another storage where the data is archived, and then on top of it, there's the sensor observation service. And for this purpose, we have been defining and implementing the C data clouds via ingestion service. That is an ingestion service that I will present later that allows to flexibly integrate different data sources in sensor web infrastructures. The sensor model language was designed for discovery of sensors, but also for the interpretation of sensor data. So you could provide metadata about sensors, like, for example, calibration information, like who is operating the sensor, additional parameters like when has it been checked for the last time, and so on. And this is quite important also to decide whether a sensor is suitable or the sensor data is suitable for your application. And also in this case, quite often still there is, you get some PDF sheets that you need to check personally, and the aim of ERML is also to provide a formal way to make it machine readable and then exchangeable between machines. Well, it's also an official ODC standard, and typical metadata elements I've already mentioned. A couple are IDs, classifiers, textual descriptions. Also important to notice that it's quite flexible regarding the outputs of senders that you could specify. You could say the outputs are encoded in CSV or in binary encoding, and that can be done using that sensor model language. What we then did was designing a sensor metadata editor. We call that Smiley, SensorML editor, and it enables the editing of sensor metadata. And coming back to the sensor observation service, it uses the sensor observation service to store the sensor information and then also later on the observations produced by the sensors. But it can also be used to push the sensor descriptions, for example, to other metadata stores. Also important to notice is, and that's why we have been doing that in cooperation with BODC, we established links to vocabulary servers operated by BODC, and that means that, for example, different sensor types are defined in that vocabulary, and we have then, for example, drop-down lists here in the editor that link directly to that vocabulary, and if you could see then the SensorML description, there's a URL pointing to the definition in that vocabulary. And that ensures to a certain extent also semantic interoperability to make sure that we are speaking about the same properties, for example, of sensors or about the same sensor types. Then, as mentioned before, the second issue was how could I publish my existing data easily in a sensor observation service or make it INSPIRE compliant by publishing it at a sensor observation service download service. And therefore, we have been investigating ways in the Horizon 2020 project, C Data Cloud, which aims to provide a pan-European infrastructure developed by data centers and institutes. So the different marine research institutes are involved across Europe. And the infrastructure is driving several portals also of the European Marine Observation and Data Network, EMODNet. And the SWI ingestion service that we have been developing facilitates the publication of observation data, heavily relying on streams. It can also be used to describe observatories, and it automatically is able to, based on the descriptions, to receive, decode, and check data. And what we aim for is that such an ingestion service is operated by the principal investigators of the observatories. So sometimes these are called research data managers or observation data managers. And it uses SensorML descriptions, that's why I've been introducing that also beforehand, for specifying the different observation structures and also the metadata. And except then also SWI-based observation data streams. This is how it looks like from the architectural view. So we may have different data sources that are providing the data, for example, MQTT brokers, where the data is pushed to from the sensors, and then it's forwarded into a source. So we are using the Spin Cloud Data Flow server, which is relying on source, processors, and sinks. And we are using then SensorML, so users can specify with the editor the different properties and outputs of the sensor, and this is then automatically interpreted here and then used to initiate such a stream processing flow here to then push the data into a database and then make it available via a send observation service. This is how it looks like here. As mentioned beforehand, you could specify the different sensor properties in the editor, and then you can also use a visual interface that is provided by the Spring framework to define the different flows for processing the data and injecting it into the database. And what's also interesting here, these processors can be quite flexible. So they can be used just for format conversion. They can also be used, for example, for quality checks or for other pre-processing steps. But as a conclusion, we think that INSPIRE provides useful guidance for handling marine observation data through sensor web standards. We have different ongoing activities. Like mentioned before, the ERML editor and the ingestion service. This is work in progress, so we are still working on it. As you have seen beforehand, we have, for example, a CSV processor, and we are currently extending the different processors that we are providing for this injection framework. And we think that the results can also be transferred to other application domains, like, for example, air quality or hydrology, for example. Thank you.
Okay, thank you. Actually, my co-authors are coming not to Europe. They are coming from Australia, New Zealand, and some of British survey and French survey. And actually, I'm not speaking just for INSPIRE data. I will speak about, demonstrate how we are building system globally, European Union, and so on. But the first question, why this presentation is INSPIRE meeting? Mineral resources are important in our everyday life in Europe, and we don't have mineral resources in Europe. And there are a list of critical minerals. There are 27 commodities in that list. And our policymakers will need information about mineral resources, national, European Union, or global level. And you may know that electric cars are coming. We will need different kind of mineral resources in that electric cars. How much lithium or cobalt we can find in Europe? Where is it coming from Congo or some other countries? Can we get that mineral resources? And my question, how we have succeeded to deliver mineral resources in national, European Union, or global level? And we published our INSPIRE data modification 5 years ago. Some projects have just started to implement that, how to build up services, and next slide will have some kind of this. The first point is that INSPIRE, the mineral resource data model, and global model, they are identical. And the first implementation of the full model of INSPIRE mineral resources actually have been implemented in these two projects. Just few countries have full data sets, and they are mainly mineral occurrences, not mines or mineral resources. And I just click these pictures. There are, like Sweden, in that service where there is no mines, Norway, Germany, and so on and so on. There are information about mineral occurrences, and then there's second one, European geological data infra. In the same way, data is missing. And now we do have first test service actually in global level, not European Union level. How to build up mineral resource data services based on EarthResourceML Lite version. It's simplified schema for INSPIRE model or this global EarthResourceML model. And this is the first picture about this implementation. And now it's under discussion, is our models too complicated? Is it difficult to implement this one? Okay, just a look, I'm not going to detail in these models. We do have a lot of models actually, and this is an extended model in one project. Do we need this kind of simplified schema? And of course, this business is global, not European Union. We will know information from Canada, Australia, North America, South America, and so on. And this mining business is global, and I have a vision in that way that we could have that kind of global service in the future. And a few words about the development of these models. Actually, this mineral resource model is an extension of Kioski ML, how to deliver geological data. And it is part of this is mineral occurrences, mines, mining activities, commodities, and so on. And it has been started in 2006 in Australia, and nowadays it's under this EarthResourceML Interoperability Working Group. And some projects, as I said, in Europe have been started to implement, like Aurora Minerals for You project, Prosum, in Australia, Oscope and Austin projects. And these models are identical, as I said. And now a few words about these models, EarthResourceML Lite and full model, and one picture from this code list. Actually, first is EarthResourceML Lite version. We published first version 2016, and last June we published second version. And in Australian service, they are actually using this EarthResourceML Lite 2.0 version. And in test version of this one geology, we are using data from circumarctic areas and Fennoscandian areas, and they are coming some data from BRCM and then New Zealand. And this EarthResourceML version 2 or INSPIRE model, minerals for EU, they have been started, as I said, but are they too complicated? And the main point is that this EarthResourceML Lite actually have all of these key elements what we do have in that full model. And it can be used to standardize actually these resource data throughout web services. I'm not going into detail in this model. This is actually the EarthResourceML Lite version. We do have mineral occurrences, commodity reserves, mining view, processing plant, mining waste, and so on. And you can find actually, first this full model. This full model have earth resource part and mining feature part. And what is inside of this, I'm not going into detail. It will take 15 to 20 minutes just go throughout the model itself. Earth resource and mining have all of these parts. And this is actually the INSPIRE full model, what is inside of this INSPIRE model or EarthResourceML model. And then code list for this EarthResourceML, EarthResourceML Lite, INSPIRE Lite in the future maybe. We do have code list for all of these geological part and mineral resource part. And you can find this global service, just clicking, today this is not working. They are just trying to construct this Australian service. And visit INSPIRE webpage, you can find information about this code list. And I just took a full list of these EarthResourceML vocabularies. There are like 20 code lists. This one is from the global service, and this one is from INSPIRE service. And one example, mine status in that global service and mine status from INSPIRE list, and they are identical. And then there is a link to these web pages where you can get detailed information about EarthResourceML or INSPIRE data specification from this, in that case, mineral resource team. And the final part, how to deliver mineral resource data in the future. Just now we have some test services in European Union, like Minerals U, Prosum, Aurora, and so on and so on. And now we are testing this global service together with Australians, New Zealand, and PGS, PRCM, and CDK. And in that case, we are using this EarthResourceML Lite version, simplified model. And now it is actually under discussion. Could we have in INSPIRE these simplified feature models in INSPIRE? Actually, if you visit this Outscene page, you can actually find data throughout the whole Australia, Tasmania. Data is coming from this Outscene portal. And actually in that portal you do have two versions, old mineral occurrence ML and EarthResourceML Lite 2.0 version in that service just now. And this is actually test version of Outscene portal, data from Outscene in one geology test. And data is coming from Australia and New Zealand. And the third party is data is coming from Arctic areas. There is a circum-Arctic data set, data from Russia, Canada, Alaska, Greenland, and all the Nordic countries are coming throughout that service. And it is a test service. It's not live just now, but it's a plan to have that first test version in one geology portal hopefully in this year. And this is a picture where the data is coming. It's coming from Australia, Nordic countries, and Arctic areas. And a few words about this test feedback, how we have managed to build up EarthResourceML Lite, full INSPIRE model, and so on. And there actually, Sweden and Finland, we have some feedback about this EarthResourceML Lite. And it seems that it's really easy and fast to build up that kind of EarthResourceML Lite version. In Sweden, they say that no major issues to build up that one, and in Finland it took 1 day to build up commodity research from our database. And then the INSPIRE full model feedback. You have to know exactly the model, how to manipulate data, and they are not so far. Like in CDK, we are using FMA, and this INSPIRE full model, and it's really complicated. You have to know model exactly and know all the part of that model. And the last picture is coming from Finland, from this commodity resource view. It took 1 day to build up that kind of service, and I hope that it will be in the full EarthResourceML Lite. Actually, I heard yesterday that BRCM has built up EarthResourceML Lite version. It's ready to come out as soon as possible. And the PG is doing the same work. And this is the last slide. Hopefully we will have that kind of mineral resource portal where we get European Union data, global data. Is it one geology or some other portal? But however, we have that kind of plan. Thank you.
Maybe a comment, Peter Baumann speaking. Thank you for this presentation. I found that very interesting. I'm busy in INSPIRE in the coverage part, and we face similar problems. INSPIRE has invested a lot into making that a nice, complicated tapestry, which actually we found unnecessary. It could be simplified, and we are working, proposing simplification. So we seem to work for similar goals, and it's very interesting for me to see that you succeeded with that you could propose a simplified and harmonized model, that both in addition. So if there's any secret to tell how to convince JRC to do that, can you please share with us?
Yeah, actually, we have done this kind of global work more than 10 years. And this global work is actually the key in that case, how we have done this kind of harmonized model from Australia, New Zealand, and Canada, Europe. And now, actually, we are trying to push this global model to this INSPIRE, because INSPIRE, mineral resource model, and global model, they are identical, this full model. And now we are trying to push that this global simplified model should be identical to this INSPIRE simplified model, so that we can have that kind of harmonized data in different services.
INSPIRE for the Carpathians in my presentation will be presented mainly as the using of the INSPIRE data for the implementation of the projects. Projects which we are conducting in UNEP Grid Warsaw, which are related with biodiversity and the spatial planning in the Carpathians. The Carpathian Convention is the framework convention on the protection and sustainable development of the Carpathians. It is an international agreement of 7 parties. And it concerning the protection and sustainable development of single mountain region, which is Carpathians. And the objective of the Carpathian Convention is cooperation of its parties and pursuing a comprehensive policy for the protection and sustainable development of the Carpathian region. Effective implementation demands the interdisciplinary approaches and collaboration, of course, and first of all needs to access to the various data, including also the geospatial data. Core thematic access for the activities conducted by UNEP Grid Warsaw are biodiversity and the conservation of the landscape values, accordingly to the Article 4 of the Carpathian Convention and Article 5 on spatial planning. Our projects are aiming, first of all, aiming to foster the spatial planning and better management of the rural areas, and the recognition of the landscape values and the distribution of green infrastructure and its role as a core element of the landscape, Carpathian landscape mosaic. How the INSPIRE works for the Carpathians? First of all, we benefit from the very broader access to the data resources, and we contribute to the enhancement of the nature and the landscape conservation by using these data and making them processed for the various purposes. Especially, it is important for the spatial planning documents, and they allow us to have the Carpathian context of the documents that usually are prepared only with the local perspective. And it is also important at the pan-Carpathian level, since this thematic data for non-EU countries can be adjusted in line with the INSPIRE rules. In our project Green Go, this is the live project, we use Green Go Carpathians. We use the following data from the national registries, and our main purpose and goal is to make the spatial plans more green. We're greening the spatial planning documents with the communes, and we use data in order to produce the new database, and which database also will give the information on the most fragmented areas and the areas that are threatened by that areas that are they have disturbed ecological connectivity. The results for stakeholders, since among these stakeholders are first of all public units, it's also at the local level and regional level. They have access to the data that we produce. First of all, we produce the complex information on current state of the land cover, the level of housing dispersion, fragmentation, and also we analyze the spatial planning documents. All of these data are accessible for the communes through the geoportal and web services. We have core benefit that data are integrated for the whole area of the Carpathian, not only with the regional context. And here are examples of these maps that were presented for the Carpathians, distribution of ecosystem types in Carpathians. We have map presenting 8 major groups of ecosystems corresponding with Korean land cover and mapped on with EUNIS habitat classification. They are available at the geoportal and with WMS and service, and now we are working on the web feature service, and also present the attributes with the information on landscape diversity indicators. Level of housing dispersion, it is quite important database that shows how the dispersion of the builded area is affecting the ecological connectivity in the Carpathians. It is the main core impact for the nature protection areas. And if we combining this data also on a geoportal. And the last database presenting fragmentation level, we have here the information about the consistency of complex area of forest and non-forest areas. And the places where the red one is the information where the built areas are affecting ecological connectivity. And if we combine this data with the Natura 2000 sites and other information on protected areas, we can first of all identify together with the local stakeholders the areas that are isolated Natura 2000 sites, and the level of these dispersed housing areas that are one of the key threats to the preservation of landscape values and ecological connectivity. And this is also the information that allows to plan how to make spatial planning more green and how to develop green infrastructure in this most threatened area. And we are doing this by mapping green infrastructure with the Carpathian local communities. Next year we will have up to 10 groups of the stakeholders, and they will conduct collaborative projects on mapping green infrastructure. They will prepare some kind of case studies on how to spatial planning can be green infrastructure can be developed at this most threatened area, and how the spatial plans can be more green and taking into account these aspects of the ecological connectivity. And finally, all of the data we can share with and integrate in the Carpathian countries integrated biodiversity information system, which is the only platform where the data on biodiversity of the Carpathians are integrated by now. And since we usually, this platform is developed in the frame of the EU funding, where the Poland is not eligible partner. So for us, it is the chance to give the input to this platform by sharing the data produced in our project on the ecological connectivity. Okay. So to sum up the most benefits of the INSPIRE in implementing Carpathian Conventions, first of all, we use the data, the INSPIRE data. We have the access to data sets and web services, and we share this data. So we use these technical recommendations and INSPIRE rules to make data available at the very low level, and also this data allow to raise awareness of the local communities and then stakeholders on Carpathian values, Carpathian landscape, also at the regional scale. Some useful links to be followed maybe later, and I think that's all.
I wondered if you could comment on whether you use the Hilux land use classification system, and whether you find any shortcomings in it. We use it and we find there are a lot of problems with the code list, and what you do about making changes that you need to it.
You mean land use for the spatial documents?
Yes,
spatial planning documents.
With the land use code list that comes with INSPIRE, which you have to use to become INSPIRE compliant, we find there are problems with the codes and how the hierarchy, the classification has been put together. I wondered if you found problems as well, and what you're doing about fixing those problems.
We focus on the classification on the built area. So you mean, as I understand, you mean how we were working with the zoning elements in this land use specification. Okay, so we don't have this Hilux classification implemented in Poland, but only because we don't have the standard for the spatial planning. So, in fact, we were using the spatial documents, spatial planning documents to reach data on the distribution of the built area. And there were no mapping on the data specification, but it was the source data to produce the information on the level of the built area and then the intensity of this built area. Yeah.
So we have an interesting lineup indeed in this session, going from sea to geology to land. And now I want to focus a little bit on agriculture, and also in another dimension. What I want to talk about is the counterpart from the high level of politics of data use down to sometimes more technical aspects. Actually, I'm going to present a project that is funded by the German Ministry of Food and Agriculture, and it goes under the fancy name of Big Picture. Okay, but before we jump into that, a little bit of motivation. There has been a nice picture lineup collected where we see how satellite data can help us. So A and B, the first two images, give us an extract of a satellite image for a particular field for a particular point in time. Okay, that's interesting for the farmers. They can see that there obviously are regions where a crop does not want to grow that much, so they can adjust their fertilizer expenditure, for example. But this is just a snapshot. So that depends, of course, on climate impacts, like how much rain has there been before, and others. Now, if we can aggregate that over time and look at the long-standing development of that field, actually we get something else. That is the far right picture that shows a so-called field potential map, where we actually have an aggregation of the potential of each place in this field. And so we get, I believe, a better picture that holds for this year from spring to fall, but also over the years, and gives good or even better information than just snapshots to the farmers. And that is something that farmers can utilize. First of all, they know their fields. If you show them such a picture, they can work with that. Second, we can start feeding automatic fertilization devices as they are produced by the John Deeres and all the others doing this machinery, and we can use that for automatic fertilizer placement and other ways. So that is something that is immediately useful for farmers. Okay, so what we want to do is obviously something like time series over satellite images, and we want to be able to analyze them from various aspects. And this is where the project comes in. Actually, it's not just about the satellite part, but it's a very important counterpart to look at the in situ truth, ground truth, and therefore it's also termed diagnosis in the field. So we want to find out if there are variations that we can spot, where do they come from, and how can we describe them quantitatively. Of course, as I said, the goal is to assist the farmers, and to this end, ground truthing is being done currently. Over 500 farmers distributed over Germany. So they all are interviewed, they have agreed to participate and to look at the images, to tell about their particular situations in their fields, so that we can calibrate and validate the satellite imagery here. This leads to a service that offers information from satellite images. You can drill down to a particular image as we have seen before, but you also can aggregate. And one particularity is that this is done via the OGC standards, which are also correlated with the INSPIRE standard, of course. Okay, and this is where the term data cube comes in, which is used in the title. So actually, this is a way to unleash our data. The data were there all the time. Like you see in the background, we had tons of files and everybody had just come and used them. Funny enough, few people did. Why? Well, because you have to find your way through Carpathian archives with strange nomenclatures that you normally don't know. The granularity is not exactly what you need. I mean, you want to get a field. Instead of that, you need to download a couple of satellite images and recompose yourself. That has prevented people from doing that. So we know already how to do seamless maps horizontally. Why not do the same thing over time? And that is the idea of the data cube, actually. There's something multidimensional that can be 3D, like a cube, yes, X, Y, and time, but you can also add height, so for example, atmospheric layers, then you get something 4D. In the end, it's multidimensional. We liberate ourselves from two-dimensional imagery, we can do that multidimensional, and then we get, for example, for each Sentinel instrument, one such data cube. So one object instead of a zillion of images. And then we can start analyzing them in space and time, as I showed in an example. And you can also start combining them. For example, weather data with satellite imagery. And that is something that we like to do in several projects. Talking about that behind, I warned you before, I'm a technologist. So I want to talk a little bit about technology. Data cubes is something that has come up these days and is quite common. Actually, we have done that since quite some time, at a time when you could not call it array analytics, when you could not call it data cubes, nobody knew that word. But raster data is something people knew. So we call it raster data manager, rasterman. And the idea is simply to have a query language on DataCube to do flexible analysis. There is an implementation with a tile streaming architecture behind, as we call it. Today we can handle regular and irregular grids with that likewise. And if you want to look at it, for example, you find it on RSTU Live. And that has brought us into standardization. I don't want to talk about all of that because time flies. Just to give you an impression how we can distribute. I said we want to combine weather data sets and satellite images. Now there are a few data centers having both. So actually we need to combine. So let us say the yellow one is say some DIAS, some Sentinel archive. Where do we get the weather data from? Well, for example, from the blue data center, could be German Weather Service, for example, or ECNWF. So what we do internally is, when we get a request for combining that, then actually we dispatch the queries, and let them work in both servers, integrate them transparently, and deliver the result to the user. As a user, you don't see where the data sit. That is all done transparently. We have done that game over more than 1,000 Amazon cloud nodes, so that works out nicely. But I don't want to talk too much about technology here. To give you an impression of what that could look like, NEO has established a service where you can, for example, combine precipitation and soil moisture and find out how that compares to the actual vegetation. So we talk about time series analysis here and fusion of time series. ECMWF likes to do river discharge, for example. And now we have somebody from Extra Europe, NCI Australia, is contributing Landsat 8 data. And that is what now we wanted to combine. So this is some screenshot of a demo. If you want to see it live, we have a booth over there. EGU in Vienna, we sent a query to ECNWF to give us heavy rainfall risk areas. Oops, precipitation data they have, but not Landsat data. However, they know a buddy in the federation, and that was NCI Australia, so they contribute their Landsat data. That was merged transparently, and with NASA Worldwind, we could display it this way. You can send the same query, of course, to NCI, doesn't matter. Now they need to fork this up query to Reading, to ECMWF for the precipitation data. Why is that good for users? Number one, you don't need to care where data sit. Number two, you are doing intercontinental data fusion, but you do not need to download yourself. You just get the result, that's all. Excuse me. That actually has shown an interesting effect, because now that we have data cubes and it's so simple to use them, we see industry taking up on this. And one example is EO Farm. That is a small company in Greece. Some of you might know one of the guys, Angelos Tsotsos, who actually is maintainer of OSU Live, is a member of that company. And they are doing big data analytics for farmers based on the standards, based on data cubes. And so they do something like vegetation index and excuse me, and per field analysis. And yes, thank you. And thanks a lot. Anybody else wants a vodka? Thank you. They're doing this, by the way, with free and with paid for data, and combining them as a service. And so band ratios are common, vegetation detection, of course, and a lot of further things. And by the way, as this turned out to work nicely, they also use the same framework now for water quality monitoring, offering additional services. So, data cubes, coming back to the headline, Actually, it is a commonly accepted step, meantime, for getting data analysis ready. And ready for analysis not just across space, but also across time. That is, generally speaking, sensor data, it's images, image time series, simulation output, like weather forecasts, or general statistical data. Actually, believe it or not, data cubes have been invented in Europe, first paper 1992. You can look it up. And rasterman is actually the European data cube engine. Today we find several of them. Research Data Alliance has done a comparison of 19 such tools that exist meantime, and I believe that's not all, there are more. And what I'm currently working on is not just on getting healthy again, it's also about establishing a European Data Cube Federation where people have their holdings, offer these holdings in the shape of data cubes into a federation so that everybody is benefiting from everybody else's data sets. We have a critical mass of people on board. We have large-scale satellite archives, so Sentinel is available. We have the German Weather Service on board, plus a few more. So we start getting a critical mass here, and that is in the spirit, I would say, of Europe. We don't like to put everything in a big pot. We want to retain our stuff, but still want or need to collaborate. And this federation allows it. You retain autonomy, while you still can benefit from each other's assets. One aspect which I could not address here is security. If I become part of such a federation, we need to talk about terms of use, about billing, etc. But this is another topic. There will be a couple of more talks this week, also in collaboration with great colleagues here, about the INSPIRE aspect. So I would very much invite you to be there or just visit us out there to discuss any possible detail. For now, thank you very much for bearing with me.
Okay, I am happy. There were before could be politically oriented presentations and technically oriented presentation, and I will try to be philosophically oriented, yes, in my presentation. People who know me, they know that I like provocate, and I will try not disappointed you. So, why I prepare my presentation? I heard first time about precision farming 25 years ago. And I have said that the progress till now is not so huge as was expected this 25 years ago. And we have to thinking why. Some 15, 20 years ago, there were opinion that farmers are old, are not so educated, but during this period, they exchange full generation. So we have a new generation, but till now, precision farming is not accepted in large scale. Where is problem? Probably in us, in the technical people. Yes, probably we are doing the mistake, and I will try to mention or show something what I see as important for this. So, there are this point, what about I would like to speak, yes, what are big data, do farmers need big data, is the wish of farmers or producers about cloud and so on. At first, what are big data? Yes, there are three topics which are usually mentioned with big data: variety, velocity, volume. I put variety at the first because if you are looking on single farm, in reality, the variety is most important on the level of a single farm because volume of other data which is managed for one farm cannot be considered as big. Okay, if you are managing all countries or continents, there is big data, but from the point of view of one single farm, it's difficult to speak about big data. Could be the data coming from machinery. The Czech average farm, which is could be 2,000 hectares, is able from machinery produce something like 20 gigabytes data per year, but in reality these are not so big data, only if you are dealing with all countries. So variety I see as most important. Now, we are very often speaking about big data as with some holy grail. It is not true. The big data could be instrument, yes, but we have to thinking about this, and there is one big question. We have rural communities. Do you think that these rural communities are interested about big data? No. It is question for other people, for IT company, researcher, advisor, developers, analytics, and economists. What is interest for this rural community? We have data. I mentioned the data, not information, not so much, but we need to look on the knowledge and wisdom which is generated from this data. This is most important because farmer need to receive information, what he has to do and why he has to do, if he has to put some amount of fertilizer and why, what is the reason that he has to put this amount of fertilizer. And this is the question for this IT company, researcher, advisor, developer, analytics, economist, and other, to be able from data generate this knowledge and wisdom which can help to the farmers. But not only farmers, because also citizens and other people are not so much interested about data, but if you are tourists, for example, you are not interested about some huge amount of the data, but you are interested about some concrete tourist object or something. So this is the way that we need to produce the wisdom and we need to deliver these things. Other important things is the return of investment. We have to thinking if in many cases it's not more dream of technical people or of producer to introduce some new technology, if it is really benefit for farmers. Yes? Because if we will introduce some excellent technology which will improve, for example, usage of fertilizer and which will increase the benefit of farmer about 10 euros per hectare, do you think that he will be willing to pay 30 euros? No. He's clever. He will never pay so much. So in many cases, we have really thinking if this new technology, new solution is benefit for farmers. If what will be really benefit for farmers from this new technology, and only in such cases, if there will be clear benefit, farmers will accept this new solution. Now I will go to one image, which is, I think, from 2008. It was done in the time frame of Future Farm project by one Danish colleague. And I like this image, and I call this image Poor Farmer, because you can see that farmer is obliged to communicate with number of information system, yes, with number of agencies, with number of users. So it was 10 years ago. What do you think with new cloud technology? Is situation for farmers better and easy? No. It became worse. We had number of information systems. Now we have number of clouds. And could be also information system. Every day there is generated thousands of different apps, etc., etc. But do you think that it is useful for a farmer to have on his mobile 1,000 apps? Every app is solving for him one concrete problem, and he needs to switch from one application to other. And for example, if he will manage machinery, he needs to go to one system. If he will manage, for example, the fertilization, he needs to go on other system. No. I think that this is not easy, and this is the problem. And what is the way? I will now show two potential ways, yes, what could be. First way I am calling the dream of big boys. So it could be big cloud provider or other, and they dream to catch all these clouds together under their own umbrella to become some who will manage all this cloud and who will deliver all this information. So this is one idea, but I think that this idea is wrong. Also due to the fact that because all these around are big boys, no from them will agree to become only part of infrastructure of some others. So probably from my point of view, this is not solution. So I see a solution other way, and I call this something like local broker. The organization who are able integrate in the region for local farmers information from these different sources and deliver this knowledge exactly for the farmer. There is also one important thing, it is trust. Yes, if there is some local broker, farmers are easy trusted with him and they are able to work with him. So this is something what I see as the future. And now we finally can come to the INSPIRE. For this, of course, it's necessary to speak about interoperability. Because if you will look now on the system of the tractors, every producer has its own standard. If we will look on different systems, there is number of standards, and if we would like to make some integration of solution, we need to speak about standards. So we are working now on some integration model, which is partly based on INSPIRE. It is extension. We call this foodie model. This model is now transferred into the ontology. We are working mainly with PSNC about this, and we are trying with this basic model to be able to integrate different information coming from different data, different measurement, Earth observation, and to deliver to the farmer some type of concrete recommendation. Of course, as was previously mentioned, Earth observation is very important. It is one from the best sources of the data for preparing recommendation for fertilization, and this is what about we are now trying to work to be able to integrate the data coming about crop types, it could be local data, data for farms with Earth observation data, and deliver to the farmer the final recommendation. I think that this is the way how we have to thinking, that we need to thinking about integration of the data. Yes, this is the important, because without this we are not able to deliver the knowledge to the farmer. Okay, it is all from my side. I think that I am in time.
Yes.
Yes, hello. Gabriele Giannini from the European Commission. Just one question when you talk about data, when you talk about the local broker, which kind of profile do you see as broker? Because I'm thinking about agronomist or
it has to be some combination of agronomist knowledge with could be expert on ICT to be able to integrate data, or data manager. So you need to try to put people together or to deliver to agronomists the tools where agronomists are able to work easy with different formats of the data. You need to have some technical data specialists behind who are able to transfer. For example, if you are working in one country, there is easy to transform country LPs to the system, and then some agronomy-oriented organization can help. Of course, there is important to have knowledge about Earth observation, about other these things to be able to provide such services. I hope that soon will start in Europe the big project Smart Agri Hub, which has to build different innovation hub in countries, and I hope that this could be the way how it could help to the local providers of such services to integrate this different information.
I would have the same question as for the previous speaker. Do you work with the Hilux land use classification system, and have you had problems with it?
I think that probably the best person to answering will be Dimitri, who is my colleague. We are integrated the data, and or Dmitry is building a huge database, open land use. We have now covered all European Union, which is based on Hilux, and he now start to build this database also for Africa. So probably if you would like to have some more technical discussion, speak with him because he knows this best.
Yes. My name is Dmitry Kozhev, and I work together with Karel and Les Project organization, and also I'm very much involved in the activities of Plan for All Association. It's basically association of organizations that try to promote some important European activities, for example, Copernicus program or INSPIRE initiative.
Use the microphone because for the filming.
Yes, sorry. And basically, time from time, we organize as Plan for All Association some hackathons, and the purpose of these hackathons is to promote basically use of European data, of Copernicus data, of some other data that is freely accessible, and also to propagate and reuse the results of some projects that are founded by European Union and that are related to geoinformational systems. And also many of organizations that are in Plan for All, they're involved in these European projects. And I think one of the big problem of European projects that it's not so often meetings of head-to-head where like organizations can work directly like together. That it's like lots of remote work, and I think it's not so efficient as work when you are all in the same place. And also these hackathons in this way is good opportunity for people from different organizations that are part of the project to get together and to work on certain pilot. And now I will present you the presentation that basically I did also, let's say, 7 months ago during the INSPIRE hack in Prague that was organized by Plan for All Association, and it's about Tuna pilot, which is under DataBio project. And there are like lots of organizations involved in this pilot. You can see them there. It's basically some logical division of work. One organization is responsible for data management, for getting data. Another organization is responsible for analyzing, processing data, visualization of the data. So it's basically just some common roles. And to define basically what is the purpose of the pilot is to create an application for fishermen in the Indian Ocean so that they can easily find where the tuna is, and they can easily navigate their ship to where tuna is. So it's basically the main requirements of this project. And basically now a little bit about technical requirements. In the ships that we are working with, they have a bunch of different screens, and for them it's important to see various information. Of course, the most important, as I said, is information about where the fish is and also about navigation route to this fish. But also for them it's very important to know the current weather conditions, the current ocean conditions, as well as some past conditions, how it was before. And also it's very important to monitor how the engine of the ship works, how much fuel it consumes, if it's like working in stable mode. Here it's basically some picture from the command room of the ship, and you can see a bunch of screens, and basically we are supposed to create some application that they will be able to divide on different screens, basically based on the information they require. And Here it's during basically this hackathon, we started to plan which information panels they will want, which should be layers on each panel, which should be sliders on each panel. And here, as I said, the first panel is most important, the distribution and route prediction, and it needs to have zoom buttons, and also it needs to have some time slider where this fisherman can go back and forth to see where they will be, where the ship will be in next hour, how the distribution of the fish will change in the next hour. Then in the second it will be some current information basically from Copernicus Marine Environmental Management Services about the current physical and biochemical characteristics of the water that it's important for them. Then it's the same panel, but for future forecast, and here it's some basically monitoring plane where you can see how the engine works, if how is the current, if the ship is going in the right direction. And here it's our user experience designer. He was making some more detailed sketches. So here is the ship. There it goes to catch fish. And you can move slider, as I told, to see how it will be in the next hours. Here is some important for them parameters from Copernicus Marine Services. Here it's predictions how it will be in the near future, and here is detailed route planning pane where you can see how the engine works, how much fuel was consumed, and so on. Then basically because it can happen that with the time for them it will be more important some other parameters. It was decided to make it more flexible because we have appropriate technologies for this. We basically, as company, less project, we are developing HS layers JavaScript library, and we create so-called map compositions. It's basically some front-end library that works with metadata catalog, and in metadata catalog you have different layers. It can be OGC services, it can be some other services that you can add to the map, and then basically you could select all services that you need in your metadata catalog and group them and put certain services in certain pane, so it can be like more flexible, and with the time if they decide or like new services appear that is of interest of them, they can just grab it from metadata catalog and put in the pane they want. Then basically it's some also functional requirement that this application needs to have at least time dimension through which you can move forward and backward. Moreover, I think it's also a requirement to have depth dimension, because also it's important to monitor all these parameters, how they change through the depths, because tuna fish doesn't just live at one dimension in the depths, it just goes up and down. So then about the space granularity, because it's basically it will be based on Copernicus Marine Services, and Copernicus Marine Services physical ones, they have granularity 0.25 degrees of 25 degrees, and then it's also important biochemical characteristics, and those services of Copernicus, they have 0.5 degrees resolution spatial. And then there are also non-functional requirements. The fleet is from Spain, from Basque Country, so it's important for them application to be multilingual. It needs to have English because it's standard international language, then Basque and Spanish because those are official languages in Basque Country. the data, what is related to ship monitoring, to how engine works, the route of the ship, it will be stored in PostgreSQL, and then the raster data that we get from Copernicus, it is stored in Razdaman database. And as front end, as I told, it will be used HS layers library. And also it needs to be elaborated on the user management, because basically it's a very, it needs to be very much thought about, because the ship is in the ocean and it's basically no police there, no nothing there, and if some third party gets data about the ship, where it goes, if it's not enough secure, it can be just overtaken by pirates, or this information where ship goes, it can be used by some competitor's company to go on the same way to catch lots of fish. And then it's like some proposed workflows that at first, basically just common sense, that at first it needs to be the application prototypes, and data needs to be collected, and it needs to be some implementation in cycles, which is quite what makes sense. And also just for my own interest, I did some research about naval maps, how they were looking before. So basically it was lots of lines of angles, because the ship, it goes by angle, so it's very important to have lines under a different angle, and then they can set the ship to go in that direction by moving this thing. Then also, as I said, it's also about angles, so that the map should be conformal with angles, so that it preserves angle, and if you draw the line under the same angle, it's represented as a straight line in the map. Then also it needs to be lots of additional data included in the application, like such topographic data about economic management zones of different countries, because different rules can be applied there. Then also it's some port infrastructure, where they can expect to see lighthouses, where they can expect other infrastructure. Here it's just some example of such important infrastructure taken from objects of OpenSeaMap. Also tidal zones are important, like tide and tide, bathymetries, and also marine traffic in the area, and weather conditions, which is obvious. And here it's just some pilot application. It's just for now at the stage of moving their HS layers library. So here it's actually real applications that you can access. For now, it just displays the most important for fishermen characteristics from Copernicus Marine Services, and you can go through time dimension, and also you can go through depth dimensions there. Basically, in future steps, we need to get the data from the fish catch, then based on fish catches and the characteristics of ocean and weather that days, we can create some model, a probability model based on machine learning, and then we can use this model to create real maps of where the catch is. And yes, it's basically more or less it. And thank you for your time, for your attention, and you're welcome to write me, ask me in person now, or just follow DataBio webpage about the progress, and also to follow Plan for All member association page to see about our future events that we do, our future hackathons, conferences. Thank you.
Just a curiosity about the INSPIRE hackathon. So can you tell us something more? How many participants?
It's usually about 30-40 participants, and it's always in a different country. For example, last one that we had, it was during OGC conference in Orléans, near Paris, and that time I think we had around 30-40 participants, and it's basically just various applications related to geospatial, common geospatial data.